Connected.
Okay.
Yeah. Okay?
Yes.
Yeah.
Now you can see my desktop, right?
Yeah, sure.
I will give you the control. Okay.
Okay, so can we start now?
Yes.
Okay.
Yes.
So today, first of all, I'd like to tell you what should be discussed today. Okay? Okay?
Yes.
Today, briefly, I will show you in PowerPoint file about the result of discussion in Tsunami JC committee. Okay?
Okay.
Especially regarding the tsunami load. Okay?
Yes.
Mainly, sorry, that's all. Regarding the questions, we have solved almost all the problems, except comment one, about the integrity between slab and Gada.
Oh yes.
Okay? And I answered to your email already, but our tsunami loading, tentative tsunami loading, is not correct. We know it already. We know it. Okay?
Okay.
So can we start from my explanation?
Okay. So now you have the control.
Yeah.
You can show your desktop.
Okay. This one? これ? Can you see the slide? あれ? どれだ?
I see my desktop. I see my own desktop.
あれ? ちょっと待って。これか。あれ? これかな?
It seems that now you are showing my desktop. So I will give you control on your desktop.
ちょっと待って。You are controlling. Okay.
Kira, so that is controlling your desktop. Click again to get your control.
Return. あれ?
So now I have the control. I want to share your desktop.
さっきの画面
Try to get it.
No, it's okay. No. I found that button to take your control or something. But
Okay, please try.
But now I'm so sorry. I pressed the button, but can you give it to me again? これ? これか. Share my desktop. Okay. あれ? どこ?
Still mine.
あれ? 違うな。How? あれ?
Okay, I will change your rule to presenter. This means I think you will show your desktop. Sharing will end if you change the presenter to Akira. So no.
Yeah. Participant.
Host. All of controls will be into so let's make you are presenter. Yes.
来た.
I think now you will show your desktop.
Yeah,
Now
okay.
I'm viewing your desktop.
Can you see the screen?
Yes, sure.
Okay. So this one. Can you see it? Can you see this PowerPoint?
Yeah, I see.
Okay. So
Yeah, I see.
later I can give you all the data in email.
Yeah.
Okay?
Thank you.
I picked up several important figures or information from JC committee material. It's okay?
Okay.
So this is Utatsu Bridge damages. Okay, so in our Tsuyagawa bridge simulation and also in Utatsu simulation, maybe this kind of how to say devices to prevent earthquake damages are important. Okay.
Yes, these
So,
devices.
yeah.
Okay, these devices are to prevent movement
Yeah,
in
yeah.
the longitudinal direction, right?
Not longitudinal.
Transversal one.
Yeah.
Really? So
Yeah.
I thought it is intentionally used for the longitudinal direction.
For example, this one, no. This is transverse direction to prevent the transverse movement due to earthquake. This one?
I see.
This one? This one?
Yeah. This is a steel one. The
Yeah,
steel,
still one. Yeah.
Yeah.
But anyway, that's detail, so let's skip that one. But anyway, that's why in Tsuyagawa simulation, we are trying to model precisely this kind of devices. Okay.
Yeah.
And one more thing, this is short length girder, right? From now S3 to S7.
Yes.
Okay.
Short one.
There's a kind of barrier to maybe to prevent falling down or something. Okay, the height of that height of barrier was around 1.5 meter or something.
So it is a solid one.
Not solid, a kind of, how do I say?
Wire.
Not wire, as for not concrete wall, not steel wall, but a kind of wall with very low stiffness.
So I think in this case it will not. I'm saying the water will not cause pressure on the bridge.
No,
due to this
no. Yeah, no. Professor Kosa said that how do I say, tsunami load on that wall should be considered.
Oh really?
Oh yeah.
So
That's why, that's also that's not important in today's discussion, but I'll tell you in detail later. Okay.
Yeah, it's 1.5 meter.
No, I'll check it later. Sorry.
Okay.
For example, Nagaoka University team and Dr. Tanaka didn't consider the effect of that wall, barrier wall. But Professor Kosa team considered the effect of that barrier wall. So that's why the results of those two teams were different. Okay.
Yes.
I'll tell you later. Okay. I'll go to next slide. So this is the simulation of tsunami by Professor Kosa team. Okay. This is Utatsu Bay, and this red dot line is Utatsu Bridge.
Yeah.
Okay.
Yeah.
I think. Sorry. This is region G, region H. In both regions, they simulated the behavior of tsunami. Okay. This graph shows the maybe minutes from when, I don't know, maybe occurrence of earthquake or something. So 30 minutes or 40 minutes after the occurrence of earthquake, and the induction height of tsunami.
I see.
Okay.
Yeah.
So in around at around 43 minutes after the occurrence of earthquake, the maximum height of tsunami was obtained in their simulation. Okay.
Yes.
This is the velocity of tsunami. Okay. So just before the maximum height of tsunami, the maximum speed of around 4 meter per second was observed. Okay? So in
Yes.
Utatsu area, the velocity of tsunami was not so large. Okay?
Yes.
First, we thought that tsunami velocity was around 6 meter per second or something. But Professor Kosa's simulation and also the video analysis support this kind of velocity for around 4 meter per second. Okay.
Yes.
The next one. This is the direction of tsunami. So I'll go back to the previous slide.
Okay.
So this area, mountain is so close to coastal line. So, sorry. This is Utatsu Bridge, but very near Utatsu Bridge, mountain exists. Okay. That's why the direction of tsunami is not like that. How do I say? Wide into left direction due to the effects of mountain. Okay.
Yeah.
So can you see the direction of tsunami? So
Yes.
not perpendicular to bridges. So you need to, how do I say, take this one into consideration. So the velocity of tsunami is not that large, 4 meter second. And furthermore, the direction of tsunami is not perpendicular to bridges. Okay. So that's why Professor Kosa, how do I say, faced a kind of difficulty to explain such kind of severe damages of the Utatsu Bridge. So former Professor Kosa's, how do I say, equation, a kind of equation to check the stability of girders, and he could not explain the severe damage of Utatsu Bridge due to small velocity and also the direction of tsunami. Okay.
Yeah.
Then looking at this figure, Professor Kosa's 3 cases. So he, how do I say, his conclusion is that he need to consider the air, okay, trapped inside, how do I say, between girders. Okay. In case 3, half of the space between girders is occupied by water. Okay. So based on this kind of assumption, he could explain the damage of Utatsu Bridge. Okay. So tentatively he is assuming 50% of void space is filled with water. Okay. So maybe in Utatsu Bridge you need to take this one into consideration. B1C.
So what is the effect of being filled with air? I mean the 50% of air.
B1C. Uplift force due to this air.
It's uplift?
Yeah. So now your assumption or our assumption is maybe case 2, right? All the spaces are filled with water. So, but more uplift force should be considered. Okay. Okay.
Yes. So you mean the height difference give another uplift like U2?
Yeah. Sure.
I see. So this finally make the bridge lighter and lighter.
Yes, you're right.
Yeah.
で、ですね、ちょっと待って、What's this? あ Okay. This one. Left. Left down figure. This one, figure 10. This is case 1, case 2, case 3. So difficult to distinguish, but the left side bar is tsunami force, action. The right side bar is resistance. Okay? So if they consider the effects of air between girders, the resistance became lower than the tsunami action. But if they, this one, no air, this is no buoyancy. Okay. So in those two cases, the resistance is much higher than the action. Okay. Of course, they, assume that the velocity of tsunami is around 4 meters per second, and they consider the direction of tsunami. Okay.
Yes. So,
but
one question.
Yeah.
Considering the tsunami wave inclined to the bridge,
Yeah.
He make he got the component vertical to the
Yes.
and make his calculation based on the perpendicular component, right?
Yeah. Sure.
Okay.
They considered only the perpendicular vertical component.
Okay,
the
but
bridge.
the one parallel to the bridge is not considered.
No.
Okay.
But several committee members recommended not only horizontal force, but how do I say, upper direction force should be considered. Some committee members said like that. But we need to continue our discussion.
Okay.
Hi.
Okay, well, one point before we move from this slide.
This one?
Okay, this one. So now we consider the drag force.
Yes.
Right? When the water velocity is constant and all the bridge is surrounded by water, right?
Yes.
But what about the surge force? The first hit or the first impact? Usually it's 50% higher than the drag force. Yeah, when the water come in the initial with the first impact.
Okay.
When the water come for first time.
Okay.
The impact force is 15. Sorry, 50.
50. Okay.
1.5. 1.5 times the drag force.
Yeah.
But of course, but also we need to know that it depends also on the water height. Maybe at this time the water height is not the maximum one.
Yeah.
So we have two variables. At the beginning, the water height is not high, but the impact force is 50% more.
Okay.
And at 45 minutes, the water wave has the highest, but no surge force. Like this. Yeah. So maybe at 30 minutes, maybe the pressure is not high, but it can be 1.5. It can be multiplied by 1.5. But at 45 minutes, it is the highest, but not multiplied by 1.5.
Yeah. But the point is that at around 30 minutes, the wave doesn't reach girders.
Yes.
Okay.
This also.
Yeah.
This is also right.
So
we have only drag force.
Yeah. We are deeply discussing, but of course there are several scenarios, not only one scenario. But in many cases, maybe impact force doesn't reach the location of girder.
Yes, it's obvious.
We have several video evidence. Gradually the height of tsunami increase. Then finally the girder will be submerged. then at the same time the tsunami velocity is increased, so maybe no impact force acted, for example, Utatsu Bridge and also Tsuyagawa Bridge.
Yes.
For several bridges, impact force, tsunami impact may affect it, but in many cases maybe no. I think so.
I see. I agree with you.
Yeah. Okay.
Okay.
So we will continue our discussion, but honestly speaking, Professor Kosa's team and another team or other teams will conduct experimental work for tsunami damage. Okay, they will investigate both of them, impact force and steady flow force.
Yeah. What is the scale of the experiment they are going to do?
Very small, but no, not very small. One institute has very good device. Of course, miniature or bridge, but they will soon conduct that kind of experiment.
Okay.
But yeah, Professor Kosa had already investigated the effect of impact force. If they consider impact force, almost all bridges will be damaged. Okay, tsunami impact force is so large, so maybe that's not true.
Yes.
Steady flow force will be the governing action, I think. Okay?
Okay.
はい。で、I'll move to Tsuyagawa Bridge.
Yes.
Okay? Now our main target. Okay? This is Tsuyagawa region and これ何つったかなI forgot the name of two, but simulation region B, C, D, F, gradually they zoom in. Okay. But using a kind of simulation technique, finally they obtained the tsunami movement in very small region containing Tsuyagawa Bridge. Okay. This is Tsuyagawa. This one. This is Tsuyagawa, and Tsuyagawa Bridge is located at the upper location in this river. Another big bridge was located in Tsuyagawa. This is Koizumi Big Bridge, Ohashi, national route. This bridge was also severely damaged. One column was missed, and steel girders were blown off 1 kilometer or something. Okay. Okay. Hi. Again, this is the simulation results of inundation height and tsunami velocity. Okay. Again, just before the maximum height, the maximum velocity was observed. But in this case, no mountain existed. This is river, Tsuyagawa. So tsunami velocity was very high, and let's say, run up of tsunami was so large. Okay.
Yes.
That's why maximum speed is also around 7.5 meter per second, something different from Utatsu region. Okay.
Yeah.
Sorry, not 1 kilometer, around 500 meters something. So this is national route, steel girders. So the direction of washing away is almost parallel to Tsuya River. But this is PC Gada's railway bridge, Tsuyagawa Bridge. A bit different from in this direction, right? So later you can know the reason. これなんだっけ津屋川のあれかあ This is the velocity near 津屋川 bridge railway bridge okay a bit located in upstream of 津屋川 bridge but again the tsunami velocity is very high nearly 7.0 meter per second okay this is the location of Gada. So finally the maximum height of tsunami was much higher than the top of the Gada. But again, so impact force doesn't work on Gada. Gradually tsunami height increase.
Yes.
And the velocity is also increased. So maybe steady flow is the main factor in this case also. Okay?
Yes.
Okay. So this is the direction of tsunami. So sorry, these dotted line are Tsuyagawa River. And
yes.
This is bridges and near here small mountain existed. That's why due to the existence of this mountain the tsunami direction is not parallel to Tsuya River but inclined to this direction. Okay? I think simulation is doing well. Can simulate the direction of tsunami well, but in reality I think more inclined. I believe. Okay. So, but anyway, but due to this inclined tsunami force, the press concrete girders were blown off into this direction. Okay. So, of course, we will utilize this information in Endo-kun's simulation. The velocity of tsunami and also the direction of tsunami. Okay?
Yeah, okay.
Okay. So that's we have more information, but that's the main knowledge, which should be fed back to you soon.
Yeah.
Okay?
Okay.
I will send you this PowerPoint file later.
Yes, please.
Okay. Regarding your comments on Endo-kun simulation, of course the I location was wrong. That was first that should be should not be in higher location. He located I location in upper position. That's why two directional force was applied. Right?
Yes.
So we will improve it soon.
Yeah, and also
Okay.
He selected all the girders, all the slab and girders, so the pressure is multiplicated. So okay. But you said you have also vertical force, or in the workshop, some researchers said they should be considered.
Yes, but I don't know how.
So, what is the source of this vertical force? I mean, how does he? I mean, is it a drag force or what kind of force? I don't know.
But one of them is buoyancy, and due to the detailed shape of Gada, maybe upward direction force into upward direction can be generated. For example, can you see this figure?
Yeah.
So, for example, the tsunami. Suppose the tsunami is comes from this direction. So due to this edge, uplift force can be easily generated, right?
Yeah.
So such kind of reason. But we do not know the extent. But anyway, maybe we should consider.
Yes. You know, also if the water height is rapidly increasing, this also may cause another kind of drag force in the upward direction from bottom to top. But if it is steady case, I mean it's not increasing very fast, so it's not a big value. But if it is increasing very rapidly from 2 meter to 3 meter to 7 meter like that, so there will be another drag force in the vertical direction. But I'm not sure how to do it here.
But it takes around 1 minute, okay, for tsunami to come up to the top of the Gada, around 1 minute, right? So I don't know. We should consider such kind of upward direction force or not.
So the height is the bridge height is around 3 meter.
3 meter.
So 3 meter in 1 minute. This is the upward velocity. So it means 3 meter. It's a very small velocity of water. 3 divided by 60. So 0.05 meter per second, which is not effective, I think. So maybe not so significant.
I also think so.
Yeah.
Okay. からCan we discuss about your comments or advices in PDF file?
Yes, please.
Okay. So actually, we could not understand sufficiently about your comment 1.
Number 1?
Yeah, integrity problem. Maybe Endo-kun has solved the problem, but he hasn't run the program after his improvement. So he can check it later. In such, So we should increase the depth of slab.
No. The point is the slab and the girders are
separated.
Are overlapping. So when you model the girder and slab, they are overlapped. So this usually make an integrity problem, and what you should do is to make slab between girders, not overlapping with girders. But because he used a rigid body, he make a rigid body for the girder and slab and all together, then this problem disappeared. But if he doesn't use a rigid body, he will have a problem. So anyway, if he I repeat again. Okay.
Oh, yeah, please.
Okay, so now we make them like 2 girders, and we want to make the slab between these 2 girders. So we should put the slab in the space between the 2 girders, because if we make it from the leftmost point to the rightmost point, it will overlap with these 2 girders. Then the software will tell you that there is an integrity problem. in this case, what you can do is to ask the software to make the intersection between the girder and slab. So one of these element will be the trimming edge, and the other will be trimmed. You can select. You can ask the ELS to make the girder as the trimming edge and the slab to be trimmed. So finally, there will be slab between the girders and not overlapping with the girders. Or the other way is to make the slab as the trimming edge, the trimming object, and the girders to be trimmed. In this case, the girder will be reduced in height by the thickness of the slab, and there will be no intersection. Or from the beginning, we make the two girders and make the slab in between. Then we avoid having such integrity problems.
Okay. I could catch only the last advice. Sorry. Anyway, okay.
Okay, so from the beginning, in the model, we avoid making overlapping between elements. So we can open ELS now and show you how to make it if it's not clear. Okay?
Okay. 開けるね。ちょっとlet's do it later.
Okay.
At the last of our discussion. Okay?
Yes, but anyway, finally, because he makes them all as rigid body, so the problem didn't affect his analysis.
Okay.
Okay.
But please check our model later.
Okay, I will also make a small presentation for this case and send you just after the meeting. Okay.
Thank you so much.
Okay.
から about the model of bearings support, okay? Well, I discussed with Endo-kun several times, and we are looking at the design drawings, and maybe you cannot understand, but we also send you the PowerPoint file later about the detailed explanation or modeling, okay?
Yeah.
Okay. これあるのかな？ある？
固定の方がいいですか？
固定でいいか。大きくしてくれる？ Can you see this one? Hamed sensei.
Yes.
Okay.
Yeah, I see.
This is his model for the fixed support. Okay. So this one, this device is modeled with steel plate, and in actual support, 2 screws are used to connect this member to this one. Okay.
Yes.
But now his modeling is the boundary of these 2 elements. I mean here is steel, so that's why the strength between these 2 elements is too strong. And in reality, only 2 screws, 2 bolts are used. Okay. So maybe we would reduce the strength considering the strength of those 2 bolts. Will soon improve. Okay. In reality, this device was broken. Maybe this is one of the trigger of the damage of Tsuyaga Bridge. Okay. But anyway, we are making this kind of model based on the real design drawings. So anyway, I'll tell you in detail later.
So this work as a hinged support?
No.
It's fixed support, right?
Fixed support, yeah. In the movable support, not hingy, and horizontal movement is allowed by some treatment. So of course we put a kind of elastic element in movable support, and of course we are considering friction between that elastic element layer. Of course, we will try to reduce the friction to almost zero. So maybe modeling of support is, how do I say, can work well, I think.
Okay.
But anyway, I will send you PowerPoint file later.
Yeah.
Hi. Maybe that's all. Maybe we have to proceed our simulation. Mainly by improving, tsunami load and detailed modeling of supports.
Yeah.
And sorry, one more question. ELS can simulate the behavior of reinforced concrete column well?
Yes.
Yes? Because
Yeah.
cracking of reinforced concrete is not easy, right? Now we are checking the correctness of ELS simulation by comparing with double comedy simulation or comp3 simulation. Now the results are not same.
So
The stiffness of ELS simulation is smaller than that of double comedy. But the maximum
double comedy is 2D, right?
yeah, right.
Maybe COP3 would be better to compare.
Yeah, but no. He is checking the performance of simple column, two-dimensional reinforcement arrangement. So not the effect of 2D.
So how far the results?
Yeah, the maximum load is almost same, but the stiffness is almost half of double comedy result.
ELS is half stiffness?
Yeah.
It's very strange.
その方が倍ぐらい。
強い。
変異は大きいです。
変異が大きいと合成弱いから。
あ
But sorry, I haven't checked the detail of his simulation, so I'll check it soon. And if I found something wrong or strange, I'll ask you.
Okay, and one more thing, you can send me the dimensions and reinforcement,
Okay.
the material properties, and we try to make it using ELS.
Okay.
And you do it with WCOM, and let's compare. I mean, we do this one, and you check this one with your calculations using WCOM.
Okay. I see.
Okay, this is also good thing.
Today that's all.
Okay, so
so
I have
あれか。
one question was in the comments we sent you in number 4.
Number 4. Okay.
There's some reinforcement.
Well,
It's not intentionally made, right?
that was his mistake. He already solved the
okay.
problem. Yeah.
Okay, and then we will do two things from our side. The first one, we do illustration for the comment number 1 using ELS, how to make it and avoid having integrity problems.
Okay.
Number 2, we will do the analysis for the column you sent us using ELS.
Okay.
From your side, we need the PowerPoint showing the details about Utatsu bridge. You should be today.
Okay.
And if possible, we do the bearing support as hinge support. We do it we simplify it using a cylinder and 2 steel plates. But we didn't make the exact model of the bearing support. So if you have details from Kosa Sensei about this one, it will be very helpful to us.
What? Utatsu bridge?
Yes, the details of the bearings.
Yeah.
We do it now in a simplified way, two steel plates with one cylinder, steel cylinder in between. So one act as a hinge, and at the end and at the other end we make it as a roller.
Okay.
So it's a very simplified one, but we don't have more details to
Yeah,
break down.
okay. Okay, I see.
So
And-
that's all. So
Yes.
yeah, and now engineer Suzanne, which is working with me in this project,
Mhm.
she's now attending also.
Susan?
So she will.
Hello?
Sorry, she is there, but she didn't speak from the beginning.
Ah, okay, okay.
So she did the most of the effort in this Utanso bridge, and she is ready to continue after getting more details.
Okay. By the way, I will visit Cairo on 3rd early morning. I will arrive in Cairo.
March 3rd.
March 3rd, yeah. And
Yeah, okay.
I will arrive at the Cairo International Airport very early in the morning, and I go directly to the hotel, but very
Yes.
near the airport. That hotel.
Novotel.
Novotel, yeah.
Yes, yes, I
Yeah.
know it.
And-
Very close to the terminal. Yeah.
And especially my family are so much worried about the safety in Egypt now. So I have reserved the hotel only for that night. I will leave Cairo on 5th early morning, around 4 a.m.
So 2 nights. You mean 2 nights?
Yeah, 2 nights. But how do I say? I can spend my time as I like in my hotel. So, one meeting. If you can have a small meeting with me,
Yeah.
I'm so glad.
We will come to you on 4th. Because right, 4th is okay, or 3rd?
Third
It
is
is
also
okay.
okay. Third is also okay. Third or
Third.
fourth. Oh. I have nothing
Okay.
to. I have nothing to do.
Okay, so
I-
we will arrange coming to you on 3rd or 4th. Don't worry. No. Yeah, actually, it's risky, but
Yeah, risky.
situation is not so
Not so severe.
difficult. I mean, for us, we can come to you, no problem. We know how to come to the hotel in a best way, avoiding the demonstration area. But for you, it is you don't know where to go. So
Yeah.
it's better for you to stay at the hotel.
Yeah.
I know. I agree with you.
Okay.
So no problem. We
Okay.
will take care of you. Don't worry.
Okay. Hi. Okay. So maybe at that time I'll bring latest information, including Endo-kun's result also.
Yeah.
Okay.
Please.
Yeah. Hi. So we will proceed the research. So
Yes.
Let's please keep in touch.
頑張りましょう。
頑張りましょう。はい。
Okay.
さよなら。
Okay. Thank you.
はい。
Bye.
はい。バイ。
Bye.
はい。